Welcome to my ramblings. This episode was long, part of an intertwined series of videos that kind of talk with the, would you say that it has an underlying theme of underlying reasons and underlying causes of things. But this one sort of takes a somewhat different tack, but I'm grouping it and putting it on YouTube at the same time as the other one. So this underlying theme is, again, underlying reasons, underlying causes. But this one is about negative sequence current, um, and I almost feel a sense of folly saying this, and unbalanced and balancing loads. Um, just coming out of the university and understanding about load diversity and stuff like that, and it's a whole different concept than how the NEC approaches the loading of equipment. You have to comply with the NEC. The NEC has adjustment factors for that you can apply to loads under very specific conditions and situations. Um, I don't remember the exact term, but it's not so much diversity, maybe diversity is wrapped in there in some sort of way, but that's the wrong book. I'm gonna go grab a copy of the NEC that I have. I want to make sure I have that term absolutely stated. I'm moving everything around. Here we go. And diversity is where when you have a large number of loads, they're not going to turn out on all at the same time. Some will be on, some will be off, and it's just uh, you know effective nature applied to a man-made system where, statistically speaking, um, you're except in extreme cases, which such as when you turn something on that's been off for a long time, that's cold load pickup, but that's a whole different chain of thought. But statistically, what happens is that you generally can rely and make engineering decisions based on that. You can, you know, you got to take into account the specific type of equipment, the number of them, and this applies to primary distribution systems. You can't do this in a building, but that you're not your peak demand is based on the diversity factors, and it's solid, um, reliable, consistent, and so engineering decisions are based on diversity factors. In the NEC, when you're sizing equipment, you're not going to have the diversity of loads because you just don't have the number of loads that you could statistically guarantee with verified, field experience that these people use to develop the diversity tables. You just don't have it. So I'm looking for section 220, 230 is services, section 225 is outside, 220 branch circuit feeders and service calculations. So I come over here, what do they call these? Demand factors. They call them demand factors. So, and I think one of the things you can rely on is that most of your lighting during the day, since it's an enclosed building, is going to be on. So don't really have much in the way of diversity, but there are some demand factors that you can apply, and maybe it's because closets are usually off, and equipment room lighting is usually off. And part of the way to train myself to quit smoking, is referenced in one of my videos, is to limit the number of ashtrays I have. I have to make a conscious effort, to go have a cigarette. That's what that's trying to force me to do. But I'll quit within 2 weeks. And well, so the thing comes up of balancing the loads. Now, this is usually some verbiage that ends up in a specification, so that, you want to make it a contract requirement that the contractor and the electrician that he's employing doesn't just, connect everything any which way. And this is sort of done when you develop a panel schedule. Um, and so when you develop a panel schedule, you try to make sure that the connected load, which is the nameplate ratings, the current that each piece of equipment is going to draw, you try to make sure that the connected load is balanced um, between the phases, so that you don't start off with all your load is connected to phase A and then nothing is on phase B. Part of the problem there is, well, if you, it's a three-phase panel. Three-phase systems are used because they deliver power more efficiently. But if you end up installing everything on phase A, then you don't get the benefit of three-phase power delivery. In other words, you're going to have return current through the neutral, and since everything's on A, the supply current coming out is going to be the same current going out on the neutral. So you try to balance the loads, and then you put a note in the specifications, contractor to balance the loads. It's kind of interesting is, when I was working at the San Carlos irrigation project, it's a it's a small agency that that is within the Bureau of Indian Affairs. I was going to say auspices of, but basically it's a Bureau of Indian Affairs agency. But Bureau of Indian Affairs falls under the Department of Interior, so I think people don't realize it. It's a federal government agency. The people working for them are civil servants, whether they're wage grade linemen, whether they're GS people doing, the billing for the electricity, and whether they're GS personnel running the place, or GM people running the place, or whether they're GS people occupying a variety of other positions, such as engineering positions. And I think I allude to just some troubling work relations with an individual. And one time he was just thinking, God, man, I don't know what it was, but I kind of felt like maybe he thought I was a clerk or I was his technician or something. So I just get all this interaction there. It's just back off. You're not my supervisor or something. I don't know. And the problem is, when I worked for the Public Works Center San Diego, they sent us to a seminar, and they're talking about, human relationships and how, in a way, people award points, for good relationships and then bad points and stuff. And so I said, okay, well, the human relation interaction between me and others, I should be assessing them, if they're going to be difficult, if they're going to call me names and stuff, they slide down my scale. If it's a good working relationship, I don't have to kiss my ass or roll out a red carpet, but there should be some respect. Which I rarely ever use that term. If they run around kicking you, tripping you and stuff, they're not going to be high up on my scale. And I think when I look back, I think what they might have been trying to say is that this was a one-way thing. We were supposed to earn points with them. It wasn't a two-way interactive thing, but such is life. I guess maybe I interpreted wrong, or maybe I'm interpreting wrong in the look back that, it was supposed to be a two-way street. So this guy is just, he's making my life difficult. It's causing me a lot of stress and stuff. So he asked this question about, hey, do you know why the wires way back in one part of the distribution system, they cross over? And the project engineer, they get, my boss's boss was there, and I'm sitting here thinking, all this stuff that this guy just slams with, it's really not work related and stuff. And I'm sitting there saying, should I reward that behavior? by telling this guy, and like, you know what, I've got to draw the line. You know, if you're going to treat me that way, I'm not going to tell you. And the project engineer, and he might have very well been right. He said, well, they probably got together and then, you know, found when the two lines came together that the phases, you know, they weren't lined up, so they had to cross them over. That's that's a distinct possibility. But the other thing, um, the other reason, the one that I had in mind, the one that I was thinking was that, well, what you do, because usually, um, you know, inductive reactance um, is affected by the spacing between conductors. And usually, a lot of times in overhead conductors, particularly when you have cross arm, almost always when you have a cross arm, not always, I have seen them try to be centered, but still, then the two end ones are further apart than, you know, any the other sets of two. And there's only three, so we're talking a subset of two, subset of two, subset of two. And so what ends up happening is if the line travels a long way, you sort of have an imbalance of inductive reactance. So, and it's due to the spacing. So I think a long, long time ago, you know, they used to interpose, I guess that's the right word, um, overhead distribution lines, like every pole, and I think and it got to every three poles. Now you just sort of, you know, because they do it now every so long distance. Um, so that was what I was thinking as to why they did it. But I was, you know, if you're going to be an asshole towards me, I can't find a justifiable reason for it. Why would I help you? Why am I gonna? That's just the point that I finally got to. And so we're out there. He might have became my supervisor at this time. I don't recall. I guess, you know, area office promoted him to the power manager and stuff. I was down at one of the switching stations, might have been a substation, and he was saying, because we have some metering systems and monitoring systems that people had done a while back, and or had started, you know, prior to my being there. And he was working on some of that stuff. And I guess what some of the metering showed him is that there was a negative sequence component to uh, to the load out there. He says we need to get rid of that negative sequence component. You need to get rid of the negative sequence component, is I think what he quote unquote said. I mean, okay. And so the problem is, you know, you go through postgraduate courses. I just ran out of money and time to finish that up. Plus, I didn't really have enough courses in power systems, I think, to get a master's degree in that. And once I relocated away, there wasn't remote classes that you could take to get a master's degree. Um, you know, at that time, it was like 2000. I think there was some. You know, the cost was just too prohibitive, and this guy, you know, I never approached the first project manager about it. Too busy settling in, but there was kind of a point where I did want to try to get a master's in power, and so I looked. They're expensive as hell, you know. So like I was going to approach that guy about taking remote courses, but so what's this issue of negative sequence? Okay, so going back to the university courses, you study load and stuff. I think some people have an idea that loads are constant all the time, and not. They change continuously, and as the loads change, you know, there's changes in voltage drop. You know, between two poles, you know, it's going to be minuscule, but you know, as loads, you know, throughout the day, constantly varying voltage because, you know, in part because the loads are constantly, you know, throughout the day. They're switching off and on as needed. You know, well, if a refrigerator doesn't run all day unless, you know, the motor's too small or it's not sized properly for its application. Pumping motors don't typically run, you know, 100% of the time. You know, there's just so many factors. So the load is constantly varying as the current that's you know, drawn, I guess, if you want to put it that way. the load current as far as constantly changing, and these aren't ideal power lines, so they do have resistive and reactive elements to them, and which means that additionally you're getting constantly changing voltage drop as well. And so although you start off trying to have your loads balanced in a building throughout the day, you know, they're never going to be balanced, but it's the best you can do really, unless you go in and do constant monitoring after it's been in service for a while, and you find out empirically that um, you know this phase for some reason all the loads, there's way more current on this one than that one, which is different from the trailer park issue that I helped resolve, in which we just had a misconnection apparently, and for some reason all the loads, uh, all the heavy loading ended up being on one phase, and after after looking at the meter printouts, we realized, okay, that all you simply need to do is to go swap this phase over that, and since it's one phase system, so it's not even three phase. It's just that for some reason, the heavy part of the load was on this phase, so let's just swap this segment of the line over to that. And as I recall, I mentioned this in one video, we actually had terminal posts that we used for terminating these, standard industry practice for that type of situation. So all I had to do was pop off, let everybody know there's going to be an outage, throw a switch or something, I guess, and then, so we're not causing a transient surge while the connection is being made. So they just pop off a separable connector, pop off the other one, problem solved. But what is negative sequence? When you have current flowing through a system, there's this thing they call symmetrical components. You can resolve it into its. Usually I deal with sequence diagrams: positive sequence resistance and reactance, negative sequence resistance and reactance, and zero sequence resistance and reactance. And but then you can also think in terms of, I have positive sequence current, I have negative sequence current, and I have zero sequence current. It's almost silly. Negative sequence current actually just represents the imbalanced current in the system. So, how do we determine? Is there anything within reasonable control where we have this distribution line going out, it's tapped off to a service transformer and stuff. It's kind of like, man, that's a massive undertaking. Well, I don't know what the extent of the imbalance was. I think general industry standard, if it's 3% or less, it's really not an issue to deal with. But this is not meant to be a negative comment towards anybody, anything like that. This is just more to illustrate, I don't, the steps we took to resolve that, determine the degree of it. That's for a different episode, but it's to point out that negative sequence current is the imbalanced current, just like as the zero sequence is the current that flows sort of effectively as a, the unbalanced, well, I don't want to say unbalanced current, but it's the current that would flow like in a line ground fault. I'm going to leave it at that because stuff gets messy and complicated, and I don't want to misspeak, but that's that. So, take the power system courses. When I modeled the entire 69 kV distribution system, you gotta know what the spacing is of all the conductors. And we didn't, we had a variety of different spacings depending on, when that part of the line was built and when it was upgraded and stuff. And so you had to know the spacing of the conductors if you're 4-pole, 4-sided thing instead of a 3-sided thing. But there is a neutral conductor as well, so 4-pole is good. But you got to know the spacing if you're going to calculate the inductive reactance. You got to know what the wire size and type is, the conductor size and type is for that portion of the segment. Because that affects incremental resistance along the line. So so I use zero sequence, positive sequence, and negative sequence diagrams. First, I had to calculate the impedance, but I calculated them as those three aspects. And then you get to the substation, you got to model the positive, negative, and zero sequence impedance of the transformers and stuff, and all that got massaged together to calculate, what our short circuit currents were. I think we had about 2,000 to 3,000 at each major substation, based on the energy provider that we get. It's based on the available short circuit energy that is available at the point where we take our power from. It traverses through the line. It's limited by by the physical lines that connect where we take power to our substations. And so then you got the primary side and secondary side. It's really surprising because I think when I did the short circuit calculations at Corpus Christi, we actually had 10,000 amps primary short circuit. I think that was 3-phase. But anyway, zero sequence current. Hope you endured the video. Television announcer, I'm not. All right. Have a nice day.